And so today we have Mike Lieberman. We'll be talking about induced and higher dimensional stable independence. So off you go, Mike. Thanks for the talk.
Thank you. So, very happy to be able to talk in this seminar. It's been a very long time. And frankly, a lot of stuff has happened in connection with the category theoretic stable independence that I'm going to be talking about. So it feels like I'm trying to pack really a lot into this talk to try to give some kind of sense of what's happened and how it leads up to the actual topic of the talk, which is this recent paper on induced and higher dimensional stable independence with applications in algebra. And as it says, essentially everything that I'm going to talk about here is joint with Jerzy Rosicki and Sebastian Basi, who sadly is no longer with us in academia. Yeah, so the focus will be on this paper, which further develops the theory of stable independence on an abstract category. And the kind of two main questions addressed there are, first, whether stable independence on a subcategory passes to category as a whole, or rather under what conditions we know that that happens. And we have a nice theorem which describes precisely those conditions. And then it turns out that there's a lot of model theoretic literature recently that shows that certain categories of algebras and modules satisfy those conditions, meaning that we can basically just grab everything they've done and get stable independence in lots of practical contexts, say torsion abelian groups with pure monomorphisms, things like that. So sort of tricky algebraic categories, tricky from the perspective of logic in that they can't be described in first order. And so the sort of basic stability theory doesn't apply. Okay, and if there's time, which I really don't think there will be, we will look at higher dimensional independence, and especially the phenomenon that model theorists refer to as excellence, where you have stable independence holding in arbitrary finite dimensions. And so I won't be sorry not to get to that, because I think we're still figuring out what it really means. On the other hand, I'm sorry not to be getting to it, because I feel like the more people that look at it, the sooner we might actually find out what it means. Okay. So in any case, I'll basically be talking about three joint papers with Jerzy and Sebastian. I've got some references at the end. At the start, just a kind of introduction. I apologize if anyone has seen this kind of spin on things, but so I'm going to try to motivate stable independence in the sense that we think about it. And one of the ways of understanding it is as a kind of robust replacement for pushouts in contexts where pushouts don't happen. And in model theory in particular, we tend not to have pushouts for the very simple reason that in model theory, we almost always work with monomorphisms. So if, for example, we're thinking about the first order theory of abelian groups, perfectly easy theory to write down, and we think about the category of models, so really, however we conceive of this, however fancy we try to be with the morphisms, if we're working model theoretically, we're basically working with monomorphisms. So of course, the category of models will be wide, but definitely not full. And this means in particular that we're just never going to have pushouts, because, if we form the pushout in the larger we'll lose some pushouts in principle, because if we take the pushout in the larger category, sure, that object will still be there, but the induced maps will not be monomorphisms. Okay, so a kind of general way of setting up this problem would be to say, okay, we have a category K and we have some family of morphisms M. How much structure do we lose if we pass to what I'm going to write as K subscript M, which is the subcategory of K on the morphisms from the family M? And of course, we can consider this at all kinds of levels of generality. One of the interesting ones is a not very general case where K is a locally presentable category. And so in this case in particular, because we have so much structure to start with, we have a lot of structure that we lose, even, it turns out, when we choose M very carefully so that KM will be a nice category. So in particular, if we manage to engineer things so that KM is accessible with all morphisms, monomorphisms, as they would be in monotheoretic applications, there's a little footnote there, which I can talk about later. I've gotten some pushback about the idea that model theory only works with monos. But if we're in that context and the category has pushouts, then it's a small category, which it's not going to be interesting, basically. Okay, so the notion of independence that I'm going to talk about, it comes from a model theoretic notion, and I'll talk a little bit about where it comes from model theoretically now, quickly. But my 2 cents is that this independence should really be understood as a kind of replacement for pushouts. So in general, we don't have pushouts in model theory, but if we're lucky, we'll have stable independence, or also called non-forking independence, which will do a lot of the same things. Okay, so here's the sort of historical development of the idea. If we're working in the first order context, we've got models of theory, we have some giant model, monster model, in which everything else sits. We talk about non-forking of a tuple of elements over a model. So the type of the tuple over a model B, we say that it doesn't fork over C if somehow when we take the type over B and the type over C, the complexity of those things is the same. Usually this would be measured in terms of Morley rank, but we don't need to worry about that. And so in first order, we can even make sense of this, not just in terms of a finite tuple on one side and a set and the monster model. We can generalize a little bit so that we've got sets all the way around. And we can really think of this as this kind of independence as an abstract ternary relation. And we can try to write down those properties, describing what it means for it to be simple in the model theoretic sense, or stable, or whatever flavor we want. And then we can go a step further. So in abstract model theory, we're not thinking about syntactic types anymore. Morley rank doesn't really make sense. You can make some kind of sense of ranks, but it doesn't work as nicely. And so really what you end up with in this case, so instead of sets arranged around this anchor, instead of talking about independence of sets, we're talking about independence of models. And really, sort of morally speaking, what we're doing is designating a family of commutative squares as being good ones, the nice independent squares. Okay. And so if you don't like that, you can forget it. But what we're going to do now is just very quickly try to mimic this in a general setting. So we're going to forget all about Morley rank and types and abstract elementary classes and whatever other nonsense, and just try to define what it means for a square to be good in that kind of sense. So really, an independence notion for us will just be a designated family of commutative squares up to, so it's sort of suitably closed. There's a little technical issue to think about. And the sort of baseline for decent behavior for one of these relations is weak stability. And we'll say that it's weakly stable if any span can be completed to an independent square. If these completions are essentially unique up to a certain notion of equivalence. And we'll also require that this family of squares be closed under horizontal and vertical composition. Was there a question, or did I? No. Okay. So we've kind of got a double category structure, just by the way. Okay, and so one of the very easy consequences of this is that if we have designated a family like this, we've got a weakly stable independence notion, then the squares will cancel the sort of familiar cancellation property of pushouts. If we've got two stuck together that are pushouts and one of them is a pushout, we can cancel it and get the other as a pushout. So just some evidence to suggest that these do some of the things we would like to do with pushouts. But that's an exceedingly weak notion. And so in fact, we want something more. And this is largely motivated by model theory, where independence is something which it has a very strong local character. It's something that's determined over small objects or small models. And we're going to impose that basically by requiring accessibility of an appropriate category. So having fixed one of these independence notions, we're going to define the category K down arrow to be, so the objects are just morphisms in the starting category, and the morphisms will be precisely the independent squares. Okay, and now we're going to start imposing sort of smoothness locality conditions. So we say that the independence relation is continuous or lambda continuous if this funny arrow category is closed under lambda directed colimits. And much stronger, we'll say that it's lambda accessible if the arrow category is lambda accessible. And really that's what we want for stability. So we're going to say that an independence relation is lambda stable if it's weakly stable and lambda accessible. Okay, so let's go back to the sort of basic problem that I set up at the beginning. We've got a category K, we've got some family of morphisms M. There's always a natural notion of independence, maybe I shouldn't say stable yet, and that is the M effective squares. So these are commutative squares of morphisms in M. The push out of the underlying span exists, and the induced map from that push out to the upper right object in our square is actually in the family M. And this is not just abstract nonsense. This actually comes out of the literature of categorical algebra. In the special case where we're looking at regular monomorphisms, these squares are exactly the effective unions of bar. Okay, so that just gives weak stability, or sorry, that just gives an independence relation. Of course, we want more than that. We'd like weak stability at minimum, ideally stability. And so we have to impose a few more restrictions on M. So here's the list of things that we want. We'd like it to be coherent in the very familiar sense. We'd like it to be what we call a co-clan, in the sense that pushouts exist and it's closed under pushouts. And I apologize for this terminology, but we say that it's almost nice if it satisfies both of those conditions, and we say it's nice if it's almost nice and it's closed under retracts. Okay, and so if we happen to have an almost nice family of morphisms at the start, the M effective squares will give us a weakly stable independence notion. So then, of course, the question becomes, what else do we need to say to get a stable independence notion? So let's go to the simplest possible special case where K is locally presentable. So, of course, as long as our family of morphisms is almost nice, as we just said, we have a weakly stable independence notion, and it's given by these M effective squares. We'd like to know when it has some of the smoothness or local character, continuity and accessibility in particular. And that's the tricky question in this context, which is very different from model theory, where verifying existence and uniqueness of an independence relation tends to be the most difficult part. So let's try to resolve this question very quickly, because I think the answer is very nice. When in this context do we get accessibility of the relation? When do we get a stable independence relation? So this is I think a very nice theorem. It's in a submitted paper, which has been knocked around a little bit in the last couple years for reasons I can't quite fathom. But so in this special case, if K is locally presentable, M is nice, and all if not continuous, then Km has a stable independence notion, just in case it has a stable independence notion given by the M effective squares, just in case the set M is cofibrantly generated and also accessible. So, I mean, some of these conditions look a bit funny, strange, nice, and all if not continuous, but it's worth noting that certainly, well, definitely if K is locally presentable, I don't think we even need that. If M is the left class of a coherent weak factorization system, then it's going to be nice and all if not continuous. So, you know, it's not the most unnatural thing in the world that we're talking about. So the proof of this uses a lot of machinery, including elimination of retracts, and a result that I'll mention in passing, which is the canonicity of stable independence. Given any category with directed bounds, so not directed colimits, but something sitting above any directed system, this a stable independence is unique. And this is confined to an appendix in one of our papers, but it's a really fascinating exercise. It shows that a lot of interesting model theory, including independent sequences, can be done in a purely abstract context. So just so you know what's there. All right. So if we get to excellence at the end, I'm going to need to come back to this. If we don't get to excellence, you can just take this as sort of an interesting side note. I want to start talking about the model theory, which ultimately is going to link to the algebra. And, you know, this is where we're going to get the most interesting results. So many of you have probably heard me talk about abstract elementary classes and are thoroughly sick of it, but let me just mention them again one more time. So this is a very straightforward generalization of the classes of models that we get in classical model theory in first order logic. It's consists of a class of structures and a finitary signature with some designated strong embeddings, with the property that those embeddings are coherent in the ambient category of structures. This family is closed under directed colimits, and then the category we get by taking just those morphisms should be accessible, which corresponds to the Levenheim-Skolem-Tarski axiom, which is basically just telling us that we can build any model or any object out of smaller things, small for some suitable sense. Okay, and I've written it here in a kind of fancy way in the the monotheoretic literature, of course, this is described in a much more straightforward fashion. These are nice, simple, concrete categories. Okay, and I'm also going to mention mu AECs, which are just like abstract elementary classes, except that we may have infinitary signature for the structures. And instead of insisting on closure under directed colimits, we may just have mu directed. Okay. So, and just as a side note, if you don't want to think about AECs or mu AECs, it's worth saying that accessible categories, all of whose morphisms are monomorphisms, are mu AECs and vice versa. So really, you can just think about that. The only trick is that to formulate the definition of types and stability in this context, we need underlying sets, so far as we know. So you should think of it as being concrete. All right, so in first order logic, we describe basically we can describe elements by types, which are just collections of formulas that they satisfy. A first order complete type would be the complete description of a tuple or an element. And we don't have syntax in this context, and so we need a sort of more algebraic looking notion, which was originally known as orbital types, but has come to be known as Galois types. And the idea is, so if we have a kind of span, like in the diagram here, we've got M1 sitting inside M0 sitting inside M1 and M2, and we have elements of M1 and M2, say A1 and A2. We say that they have the same type over M0, or they sort of have the same description over M0 if we can complete that span. Sorry, I've mislabeled these. G2 should be F2, F2 should be G2, of course. We can complete that span in such a way that it commutes and the two designated elements are mapped to the same place in N. Okay, and this is much clearer if we've got a monster model. We're just thinking about types as, we're just thinking about them as the orbits under automorphisms fixing M0. But this is the formal definition. This is one that we can make sense of in any kind of context, even if there isn't a monster model. Whether this is an equivalence relation or not, well, if we have amalgamation, basically any span can be completed to a commutative square, then it is. And even if we don't have amalgamation, we can still make sense of this. It just is less pleasant. Okay, and so in first order model theory, and even in abstract model theory, when we're thinking about AECs or mu AECs, one of the chief ways of measuring the complexity of the class of models, or the AEC or the mu AEC, is stability, which is here conceived in the sense of counting types. So in particular, we're going to say that, you know, whatever we're thinking about, an AEC, say, is lambda Galois stable if for any object of whose underlying set has cardinality lambda, there are at most lambda types over M. Okay, so stability means few types. And this is, you know, one of the hallmarks of a well-behaved theory is that it's stable somewhere. Maybe it's stable on lots of cardinals, maybe it's stable on just a few. And we should, of course, ask, how does this relate to stable independence in the sense that I mentioned earlier? Well, if we're sitting in a mu AEC with directed bounds, then if we have a stable independence relation in the sense that I've been talking about, the class will be Galois stable on a proper class of cardinals. And really, Galois stability should be strictly weaker, because among other reasons, stable independence actually implies that we have amalgamation in the underlying category. And of course, we can have Galois stable situations where there is no amalgamation. A much more interesting question would be whether there is, say, an abstract elementary class with amalgamation, which is Galois stable, but doesn't have stable independence. Okay. Anyway, let's move to this question of induced independence. So in what follows, I want to think about K as an accessible category with all morphisms, monomorphisms, which is the same as a mu AC, whichever way you want to think about it. And I'll just say, so based on our work or a few other people's, you can come up with quite a few model theoretic conditions on K that guarantee that, well, not that K has stable independence, but that there is stable independence on a nicely embedded subcategory. So in particular, well, maybe, so this might not mean anything for this audience, but the failure of the order property and a few large cardinals will give us this, or Galois stability, as we'll see, can actually, in a nice enough kind of situation, give us stable independence on the subcategory. And so this is why we ask, if we have stable independence on a subcategory, under what conditions on K and on the embedding, which I have going the wrong way, of course, L is going into K, under what conditions can we infer the existence of stable independence on K itself? Okay, so we have to, well, as currently understood, we need to assume a little bit. We can't just produce this stable independence notion out of nowhere. What we are going to need is that K is weakly stable. So this is the sort of bare minimum of assumptions on the independence relation. No kind of smoothness, no kind of locality. Well, some smoothness. So we want to assume that it's Aleph not continuous, which is to say the associated arrow category, the category of these independent squares, should have directed colimits, which of course is weaker than assuming that it's Aleph not accessible. And so even though we're assuming a fair bit here, we're not even getting close to stability itself. Okay, and we are going to need L to be a cofinal subcategory of K. And in fact, we need less than you would usually require of a cofinal subcategory. Here well, I don't know how much point there is talking through it, but we have a strictly weaker condition. So instead of insisting that we can always embed in something in the image and we can kind of amalgamate into the image, we have this, I don't even know how to describe it, really. We can compose morphisms or sequences of morphisms into the image of the functor. In any case, if we have, say, the property that any object in K can be mapped into an object with that morphism in L, then L will be cofinal in the sense that we need here. And yeah. Okay, and just some, all right. So there's model theoretic motivation for doing it this way. We don't need to look at that, I guess. And we need a little bit more, not a huge amount. Basically, we want to insist that L be accessibly embedded, which for us means full and closed under directed lambda directed colimits for some lambda. Of course, this doesn't mean the embedding is accessible. confusingly. Okay, so here's our theorem. If we are in our new context, K an accessible category with all morphisms, monomorphisms, and L accessibly embedded cofinal subcategory of K, then if K is known to have an all if not continuous weakly stable independence notion and L has a stable independence notion, then K itself has a stable independence notion. Okay, so under precisely these conditions, we can take the stable independence notion on the subcategory and we can basically just kick it up to the category as a whole. Okay. So the proof of this is fairly involved. I'll try to talk through some of it. So if we begin with the all if not continuous weakly stable independence notion on K, what we really need to do to show stability is to show that the associated category of squares is accessible. Okay, so first, all if not continuity of this relation tells us that K has to have directed colimits, which means that the subcategory, this cofinal subcategory, has to have directed bounds, which allows us to use our canonicity theorem. So the restriction of the relation on K to L will be weakly stable. This is something we have to check. But having checked that, the canonicity theorem will tell us that it, in fact, is the same as the relation that we have on L, and it's stable. Okay, and if that restriction is stable, that means it's accessible, which means that the category L itself is accessible. And now we do the usual kind of thing. We take M big enough that every category we could possibly be interested in is mu accessible. And what we're going to try to do, well, so we'll consider the set of mu-directed colimits of morphisms in this funny square category where the objects are all mu presentable. Let's call that set kappa plus. And we'd like to show that kappa plus is this, or sorry, kappa star, that kappa star is the same as the arrow category. Okay, and so like I say, this is a kind of a messy thing. We need a few little lemmas. Really, it's enough to show that the class K star is closed under composition, that it's left cancelable, and given anything in K, there's a map into something in K star where the morphism actually lives in the subcategory. Okay. So looking at the time, I don't know how much appetite I really have for a detailed explanation here. So the proof that this is enough is really just sort of a massive hodgepodge, just grabbing morphisms that we know to exist and using these properties 1 through 3. It's easy enough to read through in the paper. Maybe I won't dwell on it here. Proving those individual things is also not particularly difficult, but there's a lot of fiddling. So showing that this class is closed under composition. So we've got 2 morphisms that live in K star. We can, well, so they live in K star, so we can write them as directed colimits of the morphisms in Km. And then we can sort of monkey around with those diagrams so that the individual morphisms and the diagrams are composable enough so we can get the composition as a suitably directed colimit. I don't want to deal with 2. 3 uses an interesting result from a different joint paper mine with Yoshi and Sebastian. We basically argue by contradiction. You take a smallest m that doesn't embed in some n in k star. You can write that as a directed colimit of a smooth chain using well filtrability, which is a sort of model theory inspired property that we have in this kind of context. And then using that chain and independence, you can sort of slowly build up until you have a model from M into some N, giving you the contradiction. So for those of you who don't have me on screen right now, which might be all of you, I was sort of waving my hands around and trying to suggest what was happening there. I don't know if that will come across at all.
Mike, can I ask you a question about the statement of the theorem?
Yes.
Do you have an example of a K which has a weakly stable independence notion, which is also left zero continuous, but it is not a stable independence notion?
No.
Okay.
I don't have that. No.
And do you believe it exists?
Yeah.
Okay.
You mean, what's the question, in K or something induced? Or?
So do we have an example of K with all if not continuous weakly stable independence notion that doesn't have a stable independence notion?
No, we should, yes.
Yeah. So I 100% believe that there is such an example, but I don't.
Monomorphism in Boolean algebras or something, yes.
Oh yeah.
Possibility is not there. We should have it, I think, yes.
Yeah. No, you're right.
It's very restrictive, this accessibility condition.
Yeah. So yeah, I have already forgotten, but yeah, no, it should be. So the paper formerly known as weak factorization systems and stable independence, there should be an example in there. So that's on the archive. You would need to go back to version 2 probably to get the longer version of that paper where we think about it. But I think that's right. I think Boolean algebras are an example of this.
Okay, thank you.
Yeah. Thank you, Yoko. Okay. So enough of that. Let's think about something a little more concrete just to end with. So I said earlier that there are some model theoretic conditions that let us get stable independence on a subcategory. And I mentioned that Galois stability will do it. So to that end, we want this lemma. If we have an AEC and it has the amalgamation property, it's stable, and it satisfies another technical condition, basically telling us that types are determined over the finite. Details don't matter too much. Then there's a stable independence notion on a full cofinal subcategory. Maybe I should just say cofinal subcategory because that assumes full. And in particular, it consists of the sufficiently saturated models. And this is a pretty hairy model theoretic kind of construction. It mimics something that you see in classical model theory, where you construct stable independence over saturated models. That construction needs logical compactness very, very strongly. But some of the recent work in abstract model theory by Vasey and Boney and Grossberg show that you can essentially get away with all if not shortness, this technical condition instead. Okay, so Galois stability, at least as long as we're sitting in an AEC with amalgamation and all if not shortness, gives us basically what we need to get existence of a stable independence on, well, so it gives us stable independence on a subcategory, cofinal full subcategory, which is part of the story as far as getting stable independence on the AEC itself. But of course, we need to show that there's a weakly stable Aleph naught continuous independence notion on K before we can invoke our main theorem. And, we've got our candidate lined up already, and that's the M effective squares. So as we've already said, maybe even twice today, if we've got a category and M is an almost nice family of morphisms, then K, the subcategory of K on those morphisms has a weakly stable independence notion consisting of the M effective squares. And moreover, if M is closed under directed colimits, this independence notion will be Aleph naught continuous, which is a little annoying to prove, but true. Okay. So this basically gives us the complete story, this lemma and the main theorem. If our AEC is formed by taking a nice enough collection of morphisms and it's Galois stable and blah, 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 we are in a position to use the main theorem. And all of the examples that I'm going to show you on the next slide happen to satisfy those conditions. The slide after this one. So we're going to be using a lot of model theoretic work that has been done in the last year and a half by Tommy Kucera and Marcos Mazzari Armida, thinking about different categories of modules and groups, showing that they are Galois stable, that they are Aleph naught short, and all of these, the properties that we need. So just to give you a sense of what the argument will look like. So just one particular example, if we have a ring with unit R, the category of, say, left R modules with pure monomorphisms, pure embeddings, has a stable independence notion. So like I say, we're going to use a result of Kucera and Mazzari Armida. They've shown that this category forms an AEC. It has amalgamation, it's stable, and types are less than Aleph naught short. So the lemma gives us stable independence on a cofinal full subcategory. And then by inspection or using the fact that the pure monos are the left half of a coherent weak factorization system, we get that the pure monomorphisms are nice and closed under directed colimits. I guess the latter needs to be checked separately. Which means that the M effective squares are weakly stable, Aleph naught continuous. We apply the main theorem and boom, we have stable independence. And by canonicity, we know that the stable independence is exactly the M effective squares. I guess in this case, we would say the pure effective squares. Okay, and so now here's a big slide with categories. The exact same argument applies in each one of these cases. The model theoretic results that drive things are essentially all due to Kucera or Mazzari Armida. There are a few other things mixed in there, which I haven't kept track of properly. But, here's what we know so far. Of course, there will be other applications, but if we're working with R, an integral domain, for example, the torsion R modules with pure monos has stable independence. R divisible modules with pure monos, stable independence. In terms of groups, we can take abelian groups with monos or pure monos. We can take torsion-free abelian groups with pure monos, P groups, and so on. So really, in some sense, all of these results just fall out from our main theorem and from the work that's been done by Marcos and Tommy. All right. So I've been talking for probably long enough. Maybe I won't shift to the higher dimensional stuff because there's a good 10 minutes there. So maybe I'll stop.
Okay, thanks very much, Mike. So we can have a silent round of applause like usual. And if anyone has any questions, go ahead and ask. All right, well, if not, then let's thank Mike again.
Thank you.
And so that's it for today. So next week we have Chaitanya Subramanian from Paris giving a talk. Yep, so we can stop recording.